Okay, so let's take a look at this problem. I want to know where this function is differentiable. So differentiable means the derivative exists, right? And we know that anytime we've talked about absolute values, what do I make you do?
Draw a graph.
Okay, wait, think about what the graph does. What's an absolute value?
V.
A v. Okay, is there anywhere where you would be concerned about a derivative existing? Anything that looks kind of funny here? Maybe not. Let's kind of think. Anytime we do absolute values, remember we broke it into the piecewise. So if you put in a positive number, does the absolute value change it?
Yeah.
If I say absolute value of 3, it's still 3, right? So it's x if x is greater than 0. What happens if you put in a negative? So it's the opposite of x if x is less than 0. And equal to 0 could really fall into either of those. Let's just kind of hang back on the equal to 0 for a second. I want to look at something here. So if I were trying to find the derivative, I want to know, is it differentiable? Does the derivative exist? I would have to do the left and right hand separately here because I have two different pieces. So let's look at, let's pretend we have a positive number. So the derivative would be the limit as h approaches 0, f of x plus h, so that would just be x plus h, minus f of x, which is just x, all over h. My x's cancel. H divided by h is 1. So I get the limit as h approaches 0 of 1, which is 1. Okay, so it exists if x is positive. The derivative is just 1. All right, what if x is negative? So then we would be on the second piece. So f of x plus h would be the opposite of x plus h minus f of x, so minus negative x over h. So what happens? I'm left with negative h divided by h, which is negative 1. So this is equal to negative 1. So what I just found here is that if x is positive, my derivative was always 1. When x was negative, my derivative is always negative 1. Where is this not differentiable? Where does the derivative not exist? At 0. Reason being, do these match up? No, my left and right hand limits don't match. So we can't do it at 0. So so this function is differentiable, so the derivative exists everywhere except 0. When I look at this graph, what happened at 0? Yeah, and it was a corner. Anytime you have a sharp corner, your function is not differentiable there. Because it turns out if you have a corner, there's not a unique tangent line that we could draw there. You know, if it's curved, we could draw one, but not if it's corner. So anytime you have like zigzags and you have corners like that, every one of those corners is a place our graph is not differentiable. All right. Something else we're kind of looking at today, what makes something not differentiable. So on a graph, we have a corner. Another theorem, if the function is differentiable. So if the derivative exists, it has to be continuous there. There are places that a graph might be continuous and not differentiable, but in general, the derivative does not exist at discontinuities. So we had those on the last test. We know a discontinuity is like a break on our graph, a jump, a removable, an infinite discontinuity. Any of those places, there is no derivative. So there's no derivative if we have a corner or if we have a break in our graph. And so that's what's kind of summed up in the next few things, what makes something not differentiable. So the first one is the corner. So a corner doesn't have a tangent, so there's no derivative. We also just said if we have a discontinuity, then it's not differentiable. So corners, discontinuities. A third one is a vertical tangent line. So if your limit is going to positive or negative infinity, then the derivative does not exist. So in terms of a graph, sometimes it's easy. You can see like you would have a vertical asymptote, that's a vertical tangent line. This kind of graph, it's not quite as obvious, but this right in here turns into a vertical tangent line because it's just a very steep drop there. So this slide just kind of summarizes what makes it not differentiable. Corner, discontinuity, vertical tangent line. We can also find higher derivatives. We've only looked at the first derivative, but we can do second, third, fourth, so on. So the notation that you might see that can be written a couple different ways. You could see like y with 2 tick marks, or f double prime, or d2y over dx2. I will typically use one of these 3 notations. Basically, it's just saying you do the derivative, then you do the derivative of that answer. So we're just doing the same thing again after we get our first answer. So let's try one. Yesterday, I think in example 2, we found the derivative of x cubed minus x. So yesterday we worked this one out and we got 3x squared minus 1. Wasn't that example 2?
Oh, yeah.
So I want the double prime, so second derivative. So we just do it again. So the limit as h approaches 0, but this is my function now. So when I say f of x plus h, I'm plugging it into there. Minus f of x over h. Can I square this and distribute my 3 at the same time? So it would be x squared, so 3x squared. 2xh times 3 is 6xh. H squared times 3 is 3h squared. Minus 1. Minus the 3x squared plus 1. All over h. So then the 3x squareds cancel, the 1's cancel. If I reduce an h out of everything, I get 6x plus 3h and we get 6x for the final answer. If I asked for the third derivative, what do you think I'd do?
Do it again.
Yeah, the limit as h approaches 0 using my 6x. Okay, so any higher derivative, you're just taking your previous answer. With polynomials, they tend to get nicer the more you do them. Other functions, they can get really complicated the more we do them. So it just kind of depends if it's getting easier or harder as you go along. In terms of a graph, we said the first derivative is the slope of the tangent line. So what does the second derivative mean? So it tells us essentially the slope of the tangent line on the derivative. It's how the slope is changing in the original. So we know a derivative is a rate of change. In general, then the first derivative is telling you how the curve is changing, how the original graph is changing. Second derivative tells us how the slope is changing. When we get into more graphing, we will see what this means in terms of a graph, that it actually affects something called concavity, but we're not quite ready for that idea yet. One situation that we've used a lot, we know if we have a position function, when you do the derivative, what do you get? We had several of these.
What is that? What's it?
When we take the derivative of position, we get velocity. Okay, so velocity is like essentially our speed with direction. If you do the derivative of velocity, it tells you how your velocity is changing or how your speed is changing. Are you speeding up? Are you slowing down? What would that word be? Acceleration. Tells you how you're speeding up or slowing down. So S of t is position. Derivative of position is velocity. Derivative of velocity tells us how the velocity changes, so that's acceleration. We will typically just use these. If you're in physics, you might have heard the third derivative is called jerk. Have you guys ever talked about that?
I don't take physics.
Okay.
haven't taken it.
Okay. So at some point you might hear in your science classes the idea of jerk, but it's just the next thing. We really will just focus on position, velocity, and acceleration in here. On the next slide, I just gave you some ways, like third derivatives, 3 tick marks. After that, it kind of becomes cumbersome. So if you're going to do anything beyond the third derivative, they usually just put the number. So if I wanted the fifth derivative, I could just put a little 5 up here rather than having a ton of tick marks. But that's just our normal notation. So let's take the example we were just doing. Let's find the third and fourth derivative. So we've done first and second. We already found, remember in example 2, the first derivative was 3x squared minus 1. Example 6, we got the second derivative to be 6x. So let's find the third. So limit as h approaches 0, f of x plus h minus f of x all over h so the 6x's cancel. 6h divided by h is 6, and we just get then a derivative of 6. So the fourth. F of x plus h says go to your function, replace your x with an x plus h. There's no x, so it's just 6. Minus, what's f of x? Just 6 divided by h. So we get the limit as h approaches 0 of 0. So it just turns into a 0. And once you get to this point, any higher derivative is just going to continue to be 0. Again, not the case with every function that eventually turns into 0, but polynomials would if you did your derivative long enough. Are you okay, Emily?
Yeah, good, thank you.
You're welcome. All right. Is that okay with everybody? Let's look at a couple of the examples on here. So I worked through 2 and 6 yesterday. These are similar to some of your homework problems. Let's take a look at this one. Okay, so the graph shows us how driving speed affects gas mileage. Fuel economy is measured in miles per gallon. Speed is miles per hour. So this is the graph of F. This is telling me our fuel economy, miles per gallon. I want to know what the derivative would mean. So this is my mileage. A derivative tells you how something is changing. It's the rate of change. So what does the derivative tell us here?
The faster you go, the less gas you use.
Well, let's just keep it more general than that. Not even trying to relate to, you know, are we better off going faster or slower here? But a derivative is a rate of change. So it's telling us how F, so how the mileage, is changing depending on V, which is our speed. Okay, or you could say it's the instantaneous rate of change. It's telling us what is happening to our fuel economy. So B, I want to graph it. Now yesterday we did some examples graphing our velocities, right, or our derivatives. What did we look for first? Some of our easy things. Horizontal tangent lines. So is this going to be 0 anywhere? Looks like the only place would maybe be here. Ish. Okay, until then, it starts off increasing. It's increasing that whole time, which tells me my derivative should be positive. Notice it is kind of flattening out here, so it's still positive, but not by much. So my graph's going to kind of start off a little steeper and then be flattening out. Looks like it kind of starts flattening when we get to about here. So, you know, we're starting out, we're doing a very informal, it's kind of flattening out. And then after this, what's my graph doing? Decreasing, so it's negative. So something like that. That's really a horrible sketch, but you guys get the idea. Okay, right now, what I'm looking for on your graphs of derivatives, because we aren't finding a ton of true, accurate information, I'm looking, do you have your 0 in the right spot? Do you have your positives and negatives in the right spot? C. At what speed should you drive if you want to save on gas? So here, my derivative is positive. What that's telling me is at these speeds, my mileage is still increasing when I go faster. So whether I'm going 10, 30, 40, my mileage, maybe it's going up by less, but it is still improving as I speed up. Right here, what's happening to my mileage? It's negative. So it's telling me the faster I go, it's actually declining. My mileage is declining. So what is my optimal speed here? 55 miles per hour. It is not.
It's not even really like bare minimum highway speed.
I will say so.
This is all that counts.
Yes. All right, can you tell me where this graph is not differentiable?
3.
At 3, at 0. Why at 3?
There's a little vertical asymptote.
Not even a vertical asymptote so much, but just a,
Oh, corner.
yep. All right, what about at 0? That's kind of your vertical asymptote. We have a point, but this is also going to infinity. You could say it's a discontinuity. That would work. Either of those would be fine. All right, last example. All right, I put 4 functions up here, A, B, C, and D. Mine's prettier because it's color-coded. I want to know which is the original, first derivative, second derivative, and third derivative. So, kind of tricky. We have to take a starting point. I don't know if I want to say this. Okay, it's not always true, but if we're talking about polynomials, the more terms you have in it, the more likely it is to be the original function. Okay, not true in every type of graphing situation, but if we're looking at polynomials, the one with the most curves is probably our starting point. So based off that, which would be most likely to be our beginning one?
D.
D. Okay, so let's start here. Now we know that's not guaranteed to be the first, so we might have to put something before it. But starting at D, think about the derivative. If you want to do the derivative of D, this has a horizontal tangent line here and here, so the derivative would be 0 there. This function was increasing, so the derivative should be positive. Decreasing, so derivative is negative, and then increasing, so derivative positive. So which one should be the derivative of?
C.
Okay, so I know no matter where D falls in the list, C is the derivative of that. Okay, so if we're on C, where does this one have a horizontal tangent line? At 0. Okay, so my derivative has to be 0 there. So right now both A and B work. This graph started out decreasing and then it went increasing. So my derivative should be negative and then positive. If I'm looking at B, do we have a horizontal tangent-ish? Maybe kind of right here. But what's my graph doing the entire time? Always increasing. So the derivative should always be positive. So the derivative of B would be A. So that means D is the original, C is the first, D is the second, and A is the third. So you basically just have to pick a starting point and start figuring out which one would be the derivative from there. Is that one okay? Let's work on our homework.